Circuits, bioelectricity, and DC instruments. There's not much you can do here without a lot of practice. I will walk you through the steps here, but you're going to have to practice on some of these problems with the homework and the practice exam to make sure you understand how to do circuits in series, circuits in parallel, and then figure out the current and resistance for each thing. So here we have a series connection of resistors. That's one resistor after the other, after the other, after the other. There's certain types of, Christmas tree lights, I suppose, that are hooked up in series. When you hook them up in series, if one bulb burns out, they all go out. And it's really difficult to figure out which one burned out. Whereas if you hook up a bunch of resistors in parallel, if one of them disappeared, one of them burned out, there's still a path for the electricity from one side to the other through the remaining resistors, through the remaining light bulbs. So the other ones stay lit. So there are many circuits in which more than one device is connected to a voltage source. This is series wiring. It means that the devices are connected in such a way that there's the same electric current through each device. So all of the current that comes out of this battery has to run through resistor 1 before it then gets to resistor 2 and then continues on its path back to the battery. So when we do that, we'd say, okay, the total voltage of the battery equals the voltage drop, is what I say, the voltage drop across resistor 1 plus the voltage drop across resistor 2. So my analogy here is that we're starting at the top of the mountain at positive 3 volts, and then we're going to step down 1.5 volts, perhaps, across resistor 1, and then another 1.5 volts down to ground level across resistor 2 and back to the battery. So if we apply Ohm's law and say V equals IR, the current, it's the same current coming out of the battery through resistor 1, so V equals IR resistor 1 plus IR resistor 2 gives us I times R1 plus R2. That's how we figure out our equation here. If we hook up a bunch of resistors in series, then the series resistance is just the sum of each of those resistors, R1 plus R2 plus R3. So if I have a 10 ohm resistor plus a 20 ohm resistor plus a 30 ohm resistor, my total resistance for that circuit is going to be 60 ohms, 10 plus 20 plus 30. So that's what happens when you have resistors in series. You just add them up together. So here's an example. If we have two resistors, 6 ohms and 3 ohms, add them together. The equivalent resistance of this circuit is one 9 ohm resistor. This is important because if you said you have a 12 volt battery and a 6 ohm resistor and a 3 ohm resistor, what is the current through that circuit? It's not a one-step process. So the first thing we do is figure out the equivalent resistance, and now if I want to know the current coming out of that battery, I can say, okay, the current is going to be V equals IR, I equals V over R, 12 volts divided by the 9 ohms of equivalent resistance. That is how much current is coming out of this battery, and then I can figure out the power dissipated by each resistor and the total power delivered in that situation. So 1.33 amps is coming out of the battery flowing through each resistor. So the power consumed by resistor 1 is I squared R, the same current times the resistance of resistor 1, 10.6 watts for that guy, 5.31 watts for the other guy. Add them together and we get the total power consumed by this circuit. All sorts of applications for resistors and things of that sort. Now it gets weirder, it gets significantly stranger when we have resistors that are arranged in parallel. You can consider it to be something like this top arrangement, where I have a battery and I have two sets of wires to this battery. One that will go through this resistor R1, another one that goes through resistor R2. And if R1 wasn't there, R2 would keep going even though R1 isn't there anymore. Likewise the other way around. Now how we normally would draw it is like this. So all of the current that comes out of the battery has the option right here of going this way across R1 or that way across R2. Normally it will split and some of the current will go this way, some will go that way. But if one of them wasn't there at all, it would just all go the other way. And each resistor will draw current. Each resistor will have current travel through it as though it were there all by itself. That's what happens when you connect resistors in parallel. So we can have parallel circuitry in our house and have all sorts of electrical devices involved. Here's an analogy with plumbing, but I wanted to get to the punchline here. So again, we're going back to Ohm's law. Now we're saying the current drawn by each resistor is V over R. That means voltage times 1 over R1 plus 1 over R2. This is how we figure out parallel resistance. Now don't get this wrong. You will be tempted to. 1 over RP, 1 over the resistance in parallel, is 1 over R1 plus 1 over R2 plus 1 over R3. So if I have a 10 ohm, 20 ohm, and 30 ohm resistor hooked up here, I have to do 1 divided by 10 ohms plus 1 divided by 20 ohms. So 1 divided by 10 ohms is 0.1, right? Plus 1 divided by 20 ohms plus 1 divided by 30 ohms. And I get a number. It's really small, 0.18333. But my answer, what my parallel resistance is 1 over RP equals 0.1833. So RP equals 1 divided by 0.1833. And that's 5.45 ohms. So you have to remember to invert it at the end. Now here's the deal. The more resistors you put in parallel, the less resistance you have. Think of it this way. You take a bucket and you fill it with water and you sit it on the table. Now you poke a hole in the bucket. That is a resistor. That is a mechanism for electrons, water, to flow out of the bucket. Now if I have one resistor, there's a certain amount of water, a certain rate the water will flow out of the bucket. But if I poke more holes in there, each successive hole is like another resistor in parallel. And eventually the water's gushing out of the bucket, because the more resistors that I arrange in parallel, the less resistance I have to the flow of water. So all sorts of examples here. We want to get to this situation. Ooh, this looks terrible. We can have circuits wired partially in series and partially in parallel. So stick with me. We're up here at part A. We want to simplify this circuit by figuring out the equivalent resistance. How much current's coming out of my 24 volt battery? I have no idea. That voltage the current has to travel through the 110 ohm resistor, and then it splits into two different pathways, and all sorts of things happen. So I have to simplify this circuit. I have to take this circuit and turn it into a circuit that just has one resistor. So when I do that, I'm first going to say, okay, everything goes through this. So this 110 ohm resistor is in series with whatever comes after it. Then when I get to junction A, I have two choices. One will lead me through this 180 ohm resistor and back to the battery. So this pathway is in parallel with this pathway. So I'll jump to this pathway. This has two resistors in it. These two resistors are in series with each other. So the first step is to figure out the series resistance. Series is easy, right? I'm just adding the numbers together. 220 ohms plus 250 ohms is 470 ohms. I'll then reach in, pull out those two resistors, and replace them with just one resistor of 470 ohms. Okay, back to the drawing board. Out of my 24 volt battery, everything goes through the 110 ohm resistor because that's in series with whatever comes after it. And then I have these two parallel pathways. Parallel resistance. 1 over Rp equals 1 over 180 plus 1 over 470. And then I invert that. And it turns out that if I pull these two resistors out and replace it with the equivalent resistance, I have one 130 ohm resistor. So I've gone from this hideous mess to this significantly less hideous mess. Now I have two resistors. They're in series with each other, so I just add them together. And my equivalent resistance at the end is one 24 volt battery with one 240 ohm resistor. So current equals V over R, so I can figure out that the current through this circuit would be 0.1 amps. I'm able to do that because I figured out the equivalent resistance by simplifying a complex circuit that had both series and parallel elements. The only way that you'll get good at this is practice. So please practice. Truth be told, batteries have some amount of internal resistance, so if we want to be technical and careful as we talk about what's going on with a battery, we would have to factor that in. That's not going to be a big deal for us. All right, there's a dark world that's coming up. We call it Kirchhoff's rules. Kirchhoff's rules are for really complex circuits where we're not able to simply take a complex circuit and simplify it by way of series and parallel. We won't go too terribly in depth on this, but you do have to know a couple of things. You at least have to understand the rules. There's a junction. A junction is an intersection in the wires where the current will split off going two different pathways. Well, energy is neither created nor destroyed. That's true for electrical energy as well. So all of the electrical current, all of the current that comes into this junction has to leave the junction. It's not just going to build up and sit there. So the junction rule states that the total current directed into a junction must equal the total current directed out of the junction. So if 7 amps comes into a junction, then 7 amps has to leave. 5 amps one path, 2 amps the other path, that's legitimate. That's the junction rule. The loop rule, remember I was saying how a 12 volt battery, it's like going to the top floor. We're up at the top of the 12 volt mountain, and then as the current runs through our two resistors, 2 amps times 5 ohms, that's a 10 volt drop across this resistor. So top of the 12 volt mountain, drop down 10 volts. Across the second resistor, we have to get back down to ground level, so another 2 volts. So it turns out that as you go around this complete loop in a circuit, 12 volts here, total of 12 volts here. The sum of all of the voltage rises and drops equals 0 around any closed loop in a circuit. Now this is a really simple example that we wouldn't even bother using Kirchhoff's rules. But if we have a complex circuit, maybe something like this, now we have to say, all right, so I'm going to the top of the 24 volt mountain. I'm going to drop down across this 12 ohm resistor. Oh, what am I doing here? I'm going into the positive terminal and out the negative terminal. I have another negative drop. Maybe this is a battery charger. Maybe this is me plugging my cell phone into the wall and charging it up. So I'm charging up this battery, and then I'm dropping again across this resistor. So what I would do is say I'm going to use Kirchhoff's rules, and the sum of the voltage rises and drops. So the current through the 12 ohm resistor, so that's the voltage, V equals IR, plus 6 volts, the drop across this 6 volt battery, and this is negative. It's the potential drops on one side equals the potential rises on the other side. and then another voltage drop across this 8 ohm resistor. And it's the same current going the whole way across because this is all arranged in series, equals the 24 volt battery. So I can figure this out. Going to subtract 6 from both sides of the equation, bring this guy down to 18, and then 12i plus 8i is going to be 20i, so 18 divided by 20 give me 0.9 amps of current. Other applications of Kirchhoff's rules. So you want a strategy when you're using Kirchhoff's rules. You want to draw the current in each branch of the circuit. Choose any direction. If your choice is incorrect, then the value for the current will turn out to be a negative number, and you'll figure out that you chose incorrectly. You want to mark each resistor with a positive and negative side so you can keep track of voltage rises from negative to positive versus voltage drops from positive to negative. And then you'll apply the junction rule and loop rule in the circuit and solve these equations simultaneously for the unknown variables. We use ammeters and voltmeters to measure current and voltage and resistance. So we use digital multimeters is what we use. When you have the digital multimeter set to current, what you're going to do is have all of the current that flows through this resistor go into the multimeter and out the other side. You have to be careful when you're measuring current, because if you just touch the two probes from your ammeter to either side of the battery, you'll have infinite current flowing through the ammeter and you will trip the circuit breaker inside, blow the fuse. So voltmeter, you don't have to be careful. Once you have this set to volts, you just touch it to either side of a resistor or either side of a battery, and you measure the resistance, or no, you measure the voltage of that amount. Capacitors are opposite of resistors. So remember, resistors in parallel, 1 over R1 plus 1 over R2, etc. When you have capacitors arranged in parallel, you're going to keep increasing the capacitance. So the more capacitors you set up in parallel, the more capacitance you have. So it's like resistors in series. Likewise, if you arrange capacitors in series, you're now dividing up the voltage accessible to each of those capacitors. So each one will have less potential to store charge, and you have a smaller value. So the more capacitors in series, the less capacitance you have. There's a little experiment. Capacitors take time to charge, to store up charge, and to release charge. There is a time constant involved. So when you first turn on a capacitor, first give it access to the power source, it will build up charge from 0 to some maximum charge value, and there's a time constant, so we can figure out how long it will take for that capacitor to build up charge or to discharge. We use capacitors to store charge and to create a pacemaker to keep your heart beating regularly. Electrical grounding and more examples. All right. Do the homework. Make sure you understand this stuff. There are all sorts of YouTube videos, Khan Academy, anything, anywhere that you would want to that would help you go through DC electronics. This is ubiquitous. Hopefully you have a good starting point to be able to build off of. Okie doke. See ya.